Welcome to our fourth class. So for this class, we are going to look at properties of soil. Basically, when I talk about strength properties of soil, we're looking at determining the parameters which can be determined in the lab to be able to model the response of a soil to loading. So one of the major parameters we get from soil or from the lab is the angle of internal friction and also the cohesion. So the angle of internal friction measures the resistance of a soil against sliding, or the internal friction of soil. Then the equation C, the equation which is a force, it measures the ability for particles to hold each other. So when you have those two, you can be able to determine how the soil, or to model using some other analytical methods or empirical methods, you can substitute for those parameters to determine the bearing of a soil or to design to size a foundation. So this is a very important topic. So another thing which we are going to see in this subtopic, we are going to look at how we can predict elastic deformation, or how a material or also a response to loading in form of deformation and also stress distribution. So when you distribute a stress increase in soil, that stress increase deforms or may deform. So because soil behaves like any other material which responds to a force through the principle of Hooke's law, elasticity. When you apply a force, there will be a strain which as a result of applying a force. Now for the measure or the resistance of this material to straining, which would be the Young's modulus or elastic modulus or the resilience modulus. Is that okay? So resilience is dynamic resistance to a dynamic force to deform. So elastic and also shall come to terms which such as the and the elastoplastic material and the material which behaves in elastic and also plastic manner, which will be a soil. So those are some of the things which we are going to discuss in this chapter. So as I said that one of the things is that a soil is able to carry a load, or a soil is able to hold a load by its ability to resist that loading. So a soil should be of some strength or should be able to offer a resistance. If you go by Newton's third law of motion, that reaction is action and reaction are equal, opposite, but they are collinear. Is that okay? So that a material offers a reaction against an action. Is that okay? So a force does the same. A soil does the same. It offers a reaction. So in order to offer that reaction, it should be able to have particles which are strong enough, which are able to carry this stress or this action. So when a vertical load is applied to a dry soil, the stress is taken up by the soil skeleton or the soil minerals, the particles. Now for this stress should be taken up. Remember, soil is made of, as we say, it's made of air, water, and solids. Okay, but we say that as you already know that water cannot carry any loading. So the stress will be transferred to the solids. Yeah? Now for that stress which is offered by the soil and the reaction offered by the soil, you have to call the effective stress. Measured over a certain area to measure what we call a stress. However, if the soil is saturated, part of the stress is taken up by the soil skeleton, while the rest is taken up by the pore water pressure, which over time the pore pressure is dissipates, and then the soil skeleton takes on the loading. So that stress which is important is what we call the effective stress. So we are going to find a number of stresses. We have what we call the normal stress. The plane within a soil is a force per unit area transmitted in the normal direction across the plane. Okay, so imagine a soil is a solid. Now for the force, the stress which is imposed onto the soil when you apply a force is what called the normal stress. The vertical, which is collinear, with the application of the what? Of that force. Then we have what called the power and the water pressure. Is the pressure of water filling the voids, or the void spaces between the solid particles. The pressure. Remember, water exerts a pressure, static, hydrostatic pressure. So that pressure reduces the effective stress of soil. As you can see that the ability. So the effective stress, it represents the stress transmitted through the soil skeleton, through the stress which is responsible to carrying the load which is applied onto the soil. Is that okay? So that's what we call now for the norm. That stress, the effective stress, is equal to the total stress minus the water pressure. So this total stress we shall see is a function of density, what we call the bulk density of a soil as times the depth at which you are determining that stress. Is that okay? That will give you the total stress. Is that okay? While the effective stress we can say is equal to the submerged unit weight, or the what we call the people call the effective times of the weight minus the weight, where this one here is equal to unit saturated unit weight minus unit weight of what? Of water. So in turn, when you add this over, they will take what we call this. When you multiply times height, if you put height here, so we have saturated unit weight minus unit water pressure, which is equal to H times unit weight of water. So we have talked about the normal stress and strain. So now talk about normal stress and strain. So we say that the normal is a force per unit area. Is it okay? Now if you apply this force in direction Z, remember what this is the positive. Remember, soil in its natural form responds by compression. Is that okay? So the compressive force will be a positive force, and the tensile force. Remember, a soil cannot exist in tension. Okay, or it will break, it will separate, but it can exist in compression. We have seen what compaction is. It makes it a denser material. So we shall call that as a positive stress. So in this direction here, which is a positive direction, so we have that the force in the stress in Z is equal to the force applied in Z divided by the area of that of what we are considering, the area on which the force is being applied. Is that okay? The area on which the force is being applied, which will give us Z, and this one will give us the stress in X, and this will be a stress in direction Y. Is that okay? So this is our plane Z, plane Y, and plane X. Is that okay? And plane X. Okay. So this one, people sometimes they call it ZZ. So stress in plane. Remember the first one stands for plane. Stress in plane is Z in direction of Z. Is that okay? So we shall have our other stresses which we shall call the shearing stress. Is that okay? So and therefore, as you can see that a material, when you apply a force, there is a change. Is that okay? There is a change in this other direction. So we're saying that when you apply a material, the material is to try to compress. Okay, which this will be a positive reduction in the height of a soil sample. Now for the strain, the strain, which is a change of the deformation, which will give you change in length divided by the original length, which will be Z divided by its change in Z over Z. That will be the strain in Z. Is that okay? But when you apply a force, as we shall see, let's see if this is your material in under Hooke's law. When you apply a force here in Z, okay, it's what happened that this material will deform. If you say that it is a rigid, it is against a rigid background, this material will deform. So what do you observe? You see that in Y, there's a change in Y. There's a change. So there's a change in X. Is that okay? And also there's a change a change in z. And so here we have a change in what? A change in x. So what is how do we determine this strain? Therefore, to determine a change in y, a strain in z, in y, in x direction, as a result of application of a force in z, we shall see that we introduce what we call the Poisson ratio. Is that okay? We now for the Poisson ratio, which is our v, v is equal to the lateral strain, lateral strain. We shall see that divided by the axial strain in negative. Is that okay? Now for that it would be what does it mean? This is the axial strain in this in the direction of application of a force. It causes a deformation in x what? And that this deformation is in strain of it is negative. Is that okay? Which gives you this relation. Now for the measure of strain in axial to in lateral as a result of application of a force in this axial direction gives what called a Poisson or the deformation, the measure of that deformation or the change, the relative change in that direction as a result of application of force in what? In one other, the axial direction. So we say that this is a strain is equal to the z over y. So and that's what we have what we call the Bromic strain, which is a total of the strains in x, y, and z. And this sometimes people they call it the Bromic strain. Sometimes they call this is like that. Also remember is equal to change in volume over v. The original volume. Is that okay? Remember, if you will go to our phase relationship, we know that if you make the area constant, so that we have change in volume, which will be area. Now, if the area is constant down, if you have the uniform area one, and the only change which we're changing is height, we can say area divided by times is the change in what? The change in height divided by area times height. So this one goes that okay? And also this one is equal. Remember our volume is equal to 1 plus E. Is that okay? 1 plus E. Now for the change in volume, you find that is equal to the change in also volume is equal to change in the void ratio. So we can say that the volumic strain also can be represented in terms of change in E divided by 1 plus E naught. So we shall further see this under consolidation. That will be in our chapter 6. But I want us to recall that this also can also determine strain using what we call the change in voids within the soil. Remember, whenever a soil is compact, there is a change in volume, okay, because of water is being dissipated, and that is under normally that's under the plastic strains. So what is we have said that so we have seen that the soil shears can deform in such a form. Is that okay? Under the load we have talked about the stress in Z, which will be the force divided by the plane area, and also the strain which gives you the change divided by the original that will give a strain and stress. Well, what about now the shearing stress of soil? Remember, when you apply normally whenever you apply a normal force on a strain, what happens? The soil may fail along a given plane, shearing along a given plane. So now, if one time this, that's normal shearing, the shearing force. Is that okay? One time the normal that's shearing force. So the shear of a soil is this maximum resistance to shearing stresses. The soil shears or twists. When the resistance is exceeded, failure occurs, usually taking a form of a surface slip, as the surface is slips. So the shear stress is resisted by a force usually made up of one, the internal friction, and so the cohesion. Okay. So the ability of the particles to fuse to that twist or that shearing or that tearing, and also the cohesion, the ability of a particle to stick together. Now, if you have those two abilities, give what we call the shearing resistance. The shearing resistance. Okay, let us take this example that you are applying a shearing force in the direction what happened that the soil, if this is a particle and this is between the two particles, or the soil is shedding at this point, a defined point, what happened that you know that when you resolve the force, this is the applied normal force, but also there's a shearing force being applied. Is that okay? There's shearing force being applied, or a pulling force, or a pushing force on the soil. You have this normal force which is seated on the soil, and there's a pulling force. Is that okay? What happened that the soil, in this section, there will be a friction force which will be in this direction. So, but when you resolve this member, remember here what we have, so here we have what we call the resultant. Remember, this is a force, which is the resultant. But when you apply this force here, the normal force, so we can say tan. We have here Pn. Okay, Pn. So there will be a resultant for now. For this force here, we can say this is a force of what? F. Fa. Is that okay? So when you get tan is equal to the normal force in this direction, P divided by Fa. Because at that point, at the point at which the soil starts moving, this force here will be equal to the frictional force. Is that okay? Now for our normal force, so we are saying that the tan of theta is equal to the opposite, which is Fa divided by Pn. Okay. Now for our force, our friction force, at a point of failure, yes, and when this one is equal to that, our Fa is equal to P n, F is equal to Pn times tan of angle of friction. And that angle would have, this angle would have increased to be equal to the angle of internal friction of soil. Is that okay? Now for this, therefore the shearing stress is equal to this force, friction force, divided by area. Is that okay? So when you divide by area by this, now for this over this will give you the normal stress. The normal stress tan theta. Is that okay? So now for this equation here, give that called the normal stress, which is a component which resists the pushing or the splitting of soil. Until now, which times if you divide by the plane at which the force is applied, friction force is applied, we give that called the stress or the shearing resistance. Therefore, the shear force is a combination of both the cohesion force along that plane plus the component of a normal force along that which normally is our friction force. Okay, this is our friction. Remember, this one is a coefficient, the angle of friction of friction, and the coefficient of friction, which is tan theta. The coefficient of friction. So how do we determine these parameters? Remember, I said our shearing resistance or the shearing stress is equal to C cohesion plus the normal stress tan theta. Okay. So, but if you take this to be our y is equal to C intercept plus mx. Is that okay? So where our m is the gradient. Is that okay? Now for this one, be the gradient. Now for this one can be said it's a straight line. Where c is the y-intercept. Where x is the normal, where x is the normal. So now we can find that we can determine these parameters just from plotting a straight line and determine the intercept, which will be the c, and determining m, the gradient, which will be tan theta. Is that okay? Which will be tan theta. So we can see that the shear resistance of soil can be determined. Now this one called the failure envelope. Okay. So now for this soil can be determined from either using a direct shear stress test, or you can determine using the triaxial test from the lab to determine these parameters C, and but also it helps to determine what we call the failure envelope. Is that okay? we shall see the importance of determining the failure envelope. Now for this is our x, which is the normal stress, and this is our y, which is the shearing stress. So now what is the shear stress? So when you apply a force along a plane, a shearing or a twisting, two forces which are parallel. Is that okay? You have two forces which are parallel, applying a couple in the same direction at a fixed point. So the soil will tend to twist or to shear. Is that okay? Now for the shearing stress, which result will give you by this force divided by the plane area, which will be y times x. Okay, y times x divided by f will give the shearing force. Is that okay? Then the angle, which will be the shear strain. So the shear strain will be equal to this angle be determined by. Remember when it's twist, the swift is prefix, but you will try to twist. Okay? To twist it, as you can see, it is twisting because of the shearing at a fixed point here, because of this other twist. Now, when you get tan of this small angle, which will be equal to change in x. Remember, this is in x direction. There's a change. This is x. This is a small change in x. And divided by z. From here up here, we have our. If we put here z, divided by z. Remember, this is the shearing strain, or the shear strain. So now remember the tan of a very small. Remember these angles are very small. If you take this to be very small, now for this one so this one will turn to be the angle itself, the small angles. Remember small angles now trigonometry, which will give you change in x divided by z. Now for this one will give you the strain, or the shear strain in z, in zx direction, in the plane of z, but in the direction of x. Is that okay? We'll give you the shear, the strain. So we shall come back. All these are important. This is a deformation. Is that okay? This is a deformation by twisting. Okay? This is a deformation by twisting of, so by shearing of what? Of the soil. Well, up here we discover the failure or deformation by reduction in the height of the soil. Is that okay? What to call the normal, what to call the strain, Is that okay? The normal strains. So if, for instance, if you take a soil and you load it, you load it with the increments of a load P. Is that okay? So we have what we have seen, and the soil it will change both in when you load at this point. What happens that the soil will increase in the lateral and also in the vertical direction. It will be decreasing. Here it will increase. Is that okay? So when it increases, this is the original. When you apply a force, it will reduce. Is that okay? It reduces all this one here. It will increase. It will deform. So what happens when you start? Remember the stress you are applying in z direction will be change in P divided by the area of the sample. Is that okay? While the change in strain, in the vertical strain or the normal strain, will be the change in z divided by the original length of the sample. Okay, but also there will be a radial strain or a change in this other direction, a radial strain, which will be change in R over the original R. Now to get what called the partial ratio, we'll give you the axial strain lateral strain divided by axial, but this is a negative. Why is it a negative? Because there is an increase in this. Remember, so normally it decreases. Now for the negative, the increase is a negative, and the decrease is what? Is positive. Because normally, so when you load it, normally the convention that it will decrease. So the compression will be positive, and any tension or any increase will be a negative. That's why you have that ratio is very. Now this ratio is very important in determining the deformation properties of soil. So for common soils, we have clay soft soil, which is clay soft. Now for the partial ratio, should be normally between 0.1, 3.5 to 0.40. Okay. So for dense sand, it varies from 0.25 to 0.35. Now these are the ranges. Now for these deformations are very important. As you this value is very important in determining the deformations, especially the elastic deformations of soil, or the vertical reduction in height of a soil elastically. Okay. So imagine if we were to load this soil with increment. Is that okay? And if whenever we load this soil and unload, the soil goes and follows the same path. Is that okay? Now for that material becomes linearly elastic, like material from OA. Now if you did this in strength of materials, elastic materials. Okay, they deform, they follow the same path. But soil normally really behaves like this. A soil normally behaves as a nonlinear elastic. What does that mean? That when you load the soil with the same increment of a force, change in P, but when you unload, what happens that it doesn't follow the same path. It goes back to the original. What happened that the strains are not equal, that they change. When, for the first case here, the increase in strain, the change in Z is equal. Is equal. Now, if you load it with dp, change in P1, change in P1. After that, you get a strain. The decrease in H will be the same. It will be this. Is that okay? You determine this change in Z. And again, you will load it to change in what? In P2, where this change is same as this change. Now, when you load again with this P2, when you add an increment again here, and you calculate, you find that this is the same change of what? The change in Z is the same. So when you have that, you get what called a linear relationship. This is called the elastic material. But for a non-linear material, which is a soil, the soil behaves like this. That it goes back to if you unload it, it will go back to its original length. But when you load it to the P1, you get change. But this Z1, you get change in Z1 is not equal to change in Z2. Is that okay? After giving us this curve, it goes back to its original length, but the material is not linear. It's parabolic. Is that okay? Or it is a polynomial. It's a polynomial curve. You can say parabolic curve. Is that okay? So for such relationship is what we call the nonlinear elastic. It is elastic such that when you remove it, it goes back to its original length, but the increments of the force equal increments that do not cause the equal deformations. Okay, do not cause this equal deformations. So this we shall further. So when you divert this, when you put strain here and you put stress here, then we shall see this in